Let's get started. Hi everyone. My second talk today, for those of you who doesn't see the first talk, my name is Cagri, I'm your moderator. Today I'm going to speak about again HeatWave, but this part emphasizes the Lakehouse part. Okay, so what's special about today's talk? If you look at the data volume, there is an unprecedented increase in data volume today, right? There is around 175 zettabytes of data generated by supposedly this year, right? However, if you look at this iceberg, much of this data is really not really OLTP data, but more data like for analytics, semi-structured data, unstructured data, documents, and so on and so forth. So, and that's why we would like to address this data increase by coming up with a system within Lakehouse, within HeatWave, it's called Lakehouse, where we target terabytes and up to petabytes of data. So how does the overall HeatWave ecosystem look like? Basically, HeatWave is a one single database, one single system for OLTP, thanks to MySQL capabilities. OLAP, thanks to the talk which I gave earlier today, and then machine learning and Lakehouse. And in addition, we have new features around vector store and GenAI, which will be another talk. Your colleague will be speaking about it. So in this talk, I'll focus on the Lakehouse part. So the Lakehouse part is all about you have data in the object storage, which is a cheap storage in a cloud provider, and the data type is in various formats. It can be either in CSV, Parquet, Avro. These are the most common open data formats, as well as it can be any database export that you have taken from a different database system, or in the vector store use case, it could be documents, any sort of PDF, and so on and so forth. So let's look at the architecture overview for Lakehouse. Lakehouse consists of three components. The first component is obviously MySQL. It is MySQL based. Queries work as usual with the same syntax and so on. And you can have OLTP tables that are stored in InnoDB. How we are extending the MySQL part is with three components. The first one of them is introduction of an external table concept. In the external table concept, your data do not live in InnoDB or the MySQL server for that matter, but data is stored somewhere else. And your only metadata about the table is stored in the MySQL. And they are treated as normal MySQL tables. Secondly, we introduce a primary engine concept. So, which makes Lakehouse, HeatWave Lakehouse as the primary engine of your table. If you are creating a Lakehouse table, your primary engine is no longer InnoDB, but Lakehouse. And thirdly, we have come up with a component which is actually called autopilot. And here I'm mentioning about the auto schema part. Because your data is not structured, it's in object store, it could be in any format. We came up with utilities, tools to infer your schemas from these external files. So basically by running some simple command, you should be able to get what schema, what data types are in your table and so on, and provide these as suggestions to the user so that they can create. Second component of the overall architecture is the HeatWave compute cluster. We are reusing it as is, as in the data warehouse solution. We are storing the data in memory of the compute nodes. We are running the queries in a scalable and parallel manner on these compute nodes. And the third component, which is really important about Lakehouse, is the object storage layer. So we built a custom object storage layer on top of different cloud providers' object storage. And we primarily focused on the OCI cloud storage, or Oracle Cloud, basically, Oracle Cloud infrastructure. But we also support AWS. Here, our solution is a scale-out storage using object storage. When you have enough compute to read and write from an object store, you can basically utilize the technically infinite amount of scalability to object storage. And this is what we introduced here. It's a component called heat pump. It runs on a In fact, it runs on the same compute cluster as the HeatWave, as a separate process. You can think of it as a separate process, running one instance running on each of the compute nodes, and it accesses the HeatWave scale-out storage. And through HeatWave scale-out storage, we write data to object storage, and we read for ingestion from object storage. So how does it look? Basically, if you want to create a lakehouse table, there is a bit of a difference than creating a normal MySQL table. The difference is here basically highlighted. Engine must be a lakehouse engine, and then you have engine attributes. I'll come to that. And you define the secondary engine as rapid, meaning any query acceleration will be done through HeatWave.
Is it mandatory to have the secondary engine or not?
Well, today it's mandatory, yes. Because, I mean, like think of it, InnoDB primary engine and rapid secondary engine, so that's warehouse, right, for OLAP. And here we are saying, okay, primary engine is lakehouse, your secondary engine is rapid, meaning we still accelerate.
Yeah, but just as it is mandatory, maybe we should not even type it, right? Or
okay, yeah, that's kind of a syntactic sugar. Maybe we can take a look.
That's what I was asking.
Yeah.
Because we can have an InnoDB that is InnoDB without going to rapid, right? It's possible.
Yes.
So in this case, every time you need to have lakehouse, you need to be to use rapid. Then adding lakehouse will mean
absolutely. In fact, we are working on native SQL extensions for Lakehouse, which is an ongoing project, and we are considering this, basically removing this and automatically. Okay, so there are engine attribute parts. I mean, I don't want to go into the details, but just as a takeaway, one thing is location. You specify in object store, where can I find my source files, right? Things like, okay, my bucket in object store, my namespace, and the prefix where I can find the CSV parameters. Or similarly, you can pass a pre-authenticated request URL. So if you go to object storage for any data source there, you can create this unique URI and then pass the unique URI here so that you can load your data from there. Secondly, the file, yeah, I already mentioned. And the third one is the dialect. So this is really about your format. If you have a CSV file, then you need to specify, okay, what are my field delimiters? What are my line delimiters? I mean, what is the encoding and so on and so forth. So a bunch of parameters related to your format. So then it's 3 steps to load your data from object store into HeatWave. You essentially run today a stored procedure, which is called HeatWave load. And that goes, again, parameters I am not showing here, but it's similar to the one in the previous slide. It goes to your data in object store. It doesn't actually go all the data, but does a sampling, and based on the sampling gives you a schema suggestion, right? Okay, these are the column types, this is a schema. And then you get these DDL statements. You can then run them, essentially copy paste and run them, and your table will be created for Lakehouse. On a different table, and then when you issue alter table secondary load, you instruct the system to, okay, do the action load, fetch from object store, and then bring it into memory. You may have another table, which is backed by InnoDB, call it sales table, and you can also load it in memory. And once you do these 2 steps, you can go ahead and then run your normal join query between a InnoDB table and a data in object store in Lakehouse. And this works seamlessly.
If I don't load the data, it's just an empty table?
You'll get no wrong.
What if the data set is larger than the available memory?
Right, that's a good question. I mean, we are bound by the memory provisioned on the cluster, right? If you provision 10 node of cluster, it will be, let's say, it will be up to 10 terabytes of data that you can load. But this procedure, in addition to giving you the schema, it also tells you, hey, based on the data you provided, I think you need this big of a cluster, right? And then you can check, okay, if it is not enough, maybe you provision a bigger cluster. Okay, so as you have realized by now, loading data from object store is one of the very important points for Lakehouse, right? To be able to even come to a stage where you can issue queries, you have to bring the data efficiently. And for that, we have developed a novel mechanism for scaling out the load. Here, the idea is you have the data in user's bucket, and we have the component called heat pump. Heat pump basically is a parallel and distributed task framework, I would say, that runs on a shared nothing cluster of compute node. Before I go into the details, how we implemented scale-out load and some novel aspects, this is one example. Today we can load up to 0.5 petabyte of data into Lakehouse. And just for the reference, this runs in about 4.4 hours. And if you compare with competition there, then you will be seeing some difference. Okay, how do we achieve? Okay, it's fast, but how do we achieve it, right? So one core idea is that you can use all the compute nodes, but even that may not give you the best of worlds, right? So you have the compute nodes might be receiving some other task, let's say a query task, or maybe under memory pressure, or maybe there is a network problem on that particular node, right? So you cannot expect all of them to scale up at the same speed. And that's why we introduced this idea called super chunking. It is, in essence, or in simplified terms, it is a distributed task queue. Distributed task queue in the sense you slice your data, without touching, this is really logical slicing. You essentially list at the metadata level, okay, what are my files, what are the sizes of those, and you create logical tasks, right? Each of the unit is a data load task. And then you create many of them, B batches of K tasks each, and B is quite large, way larger than the number of nodes. And this way, there is a coordinator which does the dynamic distribution and balancing the work. It essentially assigns work to these. It's a coordinator to assign work to each of the workers on a shared nothing cluster of compute servers. Each server takes a task from this distributed task queue, does the transformation on that data. If the data is CSV, we take it, we parse it, we convert it into MySQL data, HeatWave data types, and then we create a columnar format out of it, and then we compress, and then we store these back into the object store. So this is the task of each worker. And then when they run out of work, they go back to the coordinator and says, okay, can you please give me more tasks? Or if there is one worker which is very sluggish or slow because of various reasons, then it's fine. As long as others are all occupied by the work, things will go in a scalable manner and parallelize well.
So it's kind of synchron from when you say load data to the
object
alter table or something.
Yes. It triggers this, yes.
It triggers this and then it's synchron, it waits, it sends a little bit of data, then wait that the coordinate
it's transactional, right? When you show, say, alter table secondary load, it triggers this overall process, but it waits until all the data is successfully transformed and loaded into memory.
Mm-hmm.
And this is the breakdown of that task, basically, how we achieve it, load distribution and balancing and making it parallel.
So in the MySQL stuff, it's like peer-to-peer, or it will send to all the...
So, yeah, the coordinator, it lives in MySQL node. It essentially looks at the metadata of the files from object store and then does the task computation and then communicates tasks to each of the nodes. It's connected to all of them.
Let's say that you say one of the compute node, it's very sluggish, slow. Will the coordinator, when everybody's finished and this one are still submitting?
Yeah, there will be task stealing. Yes, there will be task stealing. If this one is slow, all the tasks are finished, these other guys will say, coordinator, give me work, and the coordinator checks no more work, then it goes to other ones and then steals work from those. Yeah.
Can you choose how the data is distributed as well? Is it possible that some of the load could be skewed when you're loading it? Or is it just evenly distributed?
No, today no. We are trying to utilize all the compute nodes. So we are trying to give work to all of the compute nodes. Right. Is there more questions?
Is that in the cloud or this stuff beyond?
See?
The down layer, is it in the cloud or is
Yes,
it?
yes. It's in the OCI or AWS, wherever the compute nodes are. Okay, so that's about load. This is one of the key innovations, but also the formats we support, right? I mentioned CSV, Parquet, Avro, DB exports. Key idea, key takeaway here is no matter what the format is, we apply, I mean, depending on the format, nature of the format, we apply a different technique. For CSV, we have this innovative, speculative, distributed parsing. Well, you may think, okay, it's CSV, how complicated can it be? On a single machine, on a single core, maybe, but try to parallelize it on a cluster of nodes, and you will see really interesting problems. So this is really a nice way of parallelizing CSV parsing. And for Parquet, there is this concept of row groups. Basically, it is a unit of data within Parquet. We parallelize at that level so that we can achieve a good level of concurrency. Likewise, for Avro, it's a binary format, but this is a row major format. And there are some peculiarities, like they have sync markers across blocks. You have to figure out where are the sync markers and make sure there is no overlap between the data you assign to one worker and then the other. Right. So that's about formats. Just to give you, yeah.
Sorry. Do you perform kind of sanity check at load or at what time, for example, and does it succeed completely or it fail completely? Let's say you have 1,000 of CSV file and one row of the file 900 has one extra column that you are not expecting.
Right, right. Yes.
So does it all the load fail? Or
so for this, I mean, this is a very good example. Thanks for bringing up. We have another mode of load. It's so-called validation mode. What it does is, without loading data or without transforming, it goes over the data and then confirms whether it conforms to your schema answer. And this is much faster. Like maybe it's 1% of the actual load time. So by doing this, you can avoid such surprises. Otherwise, I mean, it's true. You can come to 99% and then see this one row.
We stopped then. We were back.
But suggestion is, or best practices is, do the validation with a huge amount of data and then.
When you are checking the stop the process, I would say, because it's different. It's per size of block or it's per row.
No, never row. We always do batch things, and
so you have like a consistent time. Whatever you have to find the rows in a block of that.
Yes, yes. It's always a block of data.
Yeah, so you can guarantee time completely.
Guarantee in terms of load time? I didn't get that.
I would say in terms of processing time, because. But let's suppose that in one row, for example, for like a month, there is like a column with a gigabyte block inside, and after that, nothing. Yes. Then the distribution is completely different.
Yes, correct. Well, okay, we are bound by some MySQL limitations, right? So columns cannot be larger than this much size and so on. So those sanity checks we can do in this validation mode and then reject straight away. But if there are things like, okay, this column was declared as date, but you found maybe something else, we can also give these errors. All right, moving on. Just wanted to show, regardless, like thanks to optimizations for each of these different formats that we support today, again, more are on the pipeline, but this is what we support. We can achieve with 100 nodes, loading of 100 terabyte of data, about 2.8 hours, more or less, and queries can work at the same speed. So why I'm showing this? It basically gives a freedom to the user. I mean, if they have CSV, it's fine. They don't have to convert into, say, Parquet, right? If they're exporting data system is generating it. Yes.
Can you do parallel query during this one?
For the unloaded tables, yes. But I mean, for this one, obviously we cannot.
So while it loads, we can still use the
Yeah. That's why I gave the example. If some compute node received a query, maybe it's under memory pressure, then it can go slower than the others and things like that. All right, so yeah, I mean, this is a little bit of, again, on the format side, we recently introduced JSON support as well. In addition to other formats I mentioned, you can have JSON as a file format, NDJSON, so new line delimited JSON, which is proving to be very common across use cases and users. We are now supporting it as well. Also, within CSV, let's say one of your columns could be JSON, so that is also supported. Likewise in PyCharm. So again, we also did a similar experiment for NDJSON, and processing speed matches what I showed for other formats. Okay, so about query processing, right? Let's say we achieve the load part, we are able to bring our data into the memory efficiently in a relatively fast manner. Then the next step is query processing. For query processing, when your data is in the database, you have a bunch of, hopefully, statistics about your data, and then your optimizer can be influenced by this. But when you are bringing data from object store, you know nothing about it. Like you may not even know the scheme of it. So then what is the key ingredient here to match the in-database performance, right? And here comes the statistics collection. So since we are doing this loading from object store, while doing it, because it's relatively a compute intensive task, we also do on-the-fly statistics generation. And I don't know if I give an example here. One example is number of distinct values, right? You look at one column and try to estimate, compute what are the distinct number of values, which later you can use in a join optimization, group by optimization, and even compression, things like that. So we do that basically while scanning all the chunks. We compute statistics, and then there is a merge phase. We aggregate those statistics into one statistics, and then write those statistics back to object store. And later in query processing, we can utilize it for optimization. And with that, again, in this chart, I just want you to focus on these first two bars. The others are a comparison with other competitors. The key message is, okay, your data in InnoDB table, you load it into HeatWave, you ran the queries, like 14 seconds average time, and then you loaded the same data from object store into memory, you run the queries, it's more or less the same. So thanks to the optimizations I've shown, you can achieve same performance, whether the data is in database or in objects. Okay, so another optimization that I can talk about is partial query execution for the data in object store. Here, okay, before this feature, the approach was you either execute everything in HeatWave or you cannot, and you rely on MySQL. But here we are choosing a different methodology. Here, let's say part of a given query can run in HeatWave, right? And then the rest of the query cannot run in HeatWave. Why would that be a case? Well, today we have a lot of good amount of coverage in HeatWave, but not everything. One example is geospatial data structures or functions, or some fancy text functions, or it could be a user-defined function. So those things can only execute in MySQL. And that's why we offload whatever portion we can offload to HeatWave and execute it there, and then ship the resulting data to MySQL and then execute the rest in MySQL. So how does it work, or how do we achieve it? Since we are a storage engine, we extended the standard MySQL engine interfaces, right? Basically starting a scan, getting the next row, and ending the scan. But before doing this, we take the queries, analyze in the optimizer phase. Okay, this is a candidate for partial execution. These parts can be executed there, and then we send it to HeatWave. And for the resulting rows, we set up this hybrid execution where we get data from HeatWave, and then rest of the execution can continue myself. Another important feature in Lakehouse, you have a lot of data in object store, but it's never static. So users will be uploading new files adding new files or deleting new files from the object store. So the idea here is we provide incremental data load into Lakehouse. For the initial load, let's say you have loaded these files, and when the customer adds new files, you also take these and incrementally update the in-memory state of HeatWave system. Here, what is the key idea? The key idea is similar to the scale-out load, but this time we only do it for the delta. Essentially, we compute the hashes of the files which we have loaded, and we keep track of those in a metadata. And then on a refresh command, this is, by the way, today a manual operation, user issues a refresh. On that operation, we go through the list of files in object store. And if you identify one file is a new file, then we trigger a scale-out heat pump transformation. And this is treated as a new slice in the table, and that is added atomically to the table once the transformation phase is done.
Is there any level of consistency?
Yes, it's a snapshot isolation, read committed. All right, so yeah, it's a delta design, as I mentioned. Thanks to this, it also scales out. If you are inserting like a bulk insert, let's say 10 terabyte data in the initial load, maybe 1 terabyte added, and you issue a refresh, that also scales thanks to this. Deletes are much simpler because for deletes, we can track from in memory, okay, this data belongs to this row, and this file is, okay, it belongs to this file, and this file is deleted in object store, then it's a matter of really dropping it from main memory. We don't really need to do anything fast. Yes?
While you do the refresh, can you query the data?
The same table, yes, you can. But as of the transaction time, you will see when the query entered the system, right? You will see that version. It's MVCC based. But if the update is ongoing, and that is applied and committed, only after that point onwards you will see the new version.
I will play the devil's advocate here. You know, when I see that, then I say, okay, let's load a very few amount of data, and then chunk myself, and then just add them, refresh, add them, refresh, and then it may take a bit longer than load all my data, if it will be accessible at the end.
But you get incremental query results, right? I mean, whether it's a use case, this is just addresses or not.
When you are in your MySQL, you do start transaction. You run some kind of query, takes a transaction of all the heat pump memory distance and the local MySQL, so that everything is like snapshot isolated. Is that correct?
Okay, so how it happens is you issued alter table secondary load, right? So this is a full load. Let's say you put portion of your data in object store and you issue this.
Yeah.
Once
someone else is entering the system, change, for example, load the
yes. But first load needs to finish first, right? To be able to refresh. First, let's assume first load finished. You have some data in memory. That you can already start querying. And then somebody added new data and they should refresh. Only if that refresh commits and finishes, you will see the new data. Otherwise, you will still see the old data, whatever you do.
So you basically have a synchronized transaction around all the system.
For the refresh operator, there is a transaction guarantee. Yes. Okay, so that's about incremental refresh. One more new feature is exporting data to object store. You may think why this is useful. And by the way, we introduce a sort of a new syntax for this. You can write a SQL query and say into out file, and you specify object store parameters like bucket or URI and so on, and given in a format like a JSON, Parquet, and so on, and you write whatever query you are running, let's say a very expensive join query or group by query, take the result of that and then write into object store in the format that we request. And then what happens is, then whatever data you wrote, you can load it again, and then maybe it's sort of a materialized view, right? You can write something and load it into Lakehouse again, and then the query processing. So this proves to be a very efficient feature. And while doing this, we are also utilizing the parallelism. We use all the code, all the compute nodes to write and generate the results in a parallel manner.
Does it work only with data that you have already in HeatWave or in Lakehouse, or does it work like with InnoDB data that I want to store in a
Right. So this feature is developed as an overall project to support everything. But today, HeatWave backend is implemented. InnoDB part is we are working.
And what is the final idea? To give the MySQL premise to the clients, and then you can connect to the cloud, or is it like the MySQL needs to be also in the CI?
No, I mean, this data is obviously from cloud, right? You can export it to object store of your choice. And from there, it's up to you what you want to do with that data. I mean, you can move it to your on-premise or put it to another cloud provider.
But could we do the reverse? So
Yeah.
from on-prem, when the InnoDB part it's finished, do a select.
Yeah, we are relying on inbound replication for that. Maybe that we can. All right, so I'll take a few more minutes. One thing is autopilot. Again, I'm not mentioning all features of autopilot. It has more things to do, but one thing is really generating schema from data files. The stored procedure I have already showed, the HeatWave underscore load, and you point only to the location in your object store, and it goes through those and generates this DDL for you with all the types, whether it's a not null, and so on and so forth, and all the attributes filled in. And if you like it, then it's a matter of just putting this into your database and then create it and start loading. This is also a challenging task in the sense you can scan all the data and then you know with 100% precision that, okay, you know the schema. Okay, when I'm saying this is the not null column, I know 100%, but I have to scan all the data, right? The challenge is, can you do this without seeing all the data? And the answer is yes, but again, it's still probabilistic. There is maybe 1% or 0.91% things may go wrong, but we achieve it by using an adaptive sampling. The essence of the idea is you get data and you look at the statistics, right? For this column, I'm assuming, okay, this is an int32. I see more data, and at some point it hits a plateau that I cannot change my decision anymore. Like I have seen enough data, then I decide this is int32. Or likewise, I have not seen any null value for this, so then I think it's a not null column. Yeah, this is how it works. If you look at the data sizes for half a petabyte data, this finishes in less than a minute. So without adaptive sampling, this would not be possible, obviously, but the trade-off is you have some probabilistic mistake, but in return you get this very, very nice runtime of detecting the schema.
It's only the head of the fact, or you go to the whole process and just pick a sample?
Yeah, it's an adaptive sampling. Basically, it uses some statistic sampling technique. It samples, but as it samples, it keeps track of, okay, what are my thresholds, and so it dynamically adjusts, right? If you have a skewed data distribution, then maybe it will see more data, but if it's uniform.
Yeah, it goes through the whole data, but it just get the statistic based on.
No, it doesn't go through the whole data. It samples data. Like if you have thousands of files, maybe it will pick 10 files out of this.
Yeah.
All right, so just 2 more slides. I think there will be a talk by Miloš on this vector store processing, but just to give you an idea, we have a now native vector data type in both MySQL and HeatWave. And when we store on HeatWave in memory, it's obviously columnar and benefits from all the nice features of HeatWave. And secondly, for vector processing, if you have some SQL query like this, distance calculation, by the way, we support all of these distance calculations, commonly used ones. This calculation will benefit from SIMD instruction processing and really processes at near memory bandwidth. Yeah, I'll just skip this, leave it for Miloš to talk about it, and just come to my conclusions. I presented HeatWave Lakehouse. It's part of a converged single system for OLTP, SQL Analytics, Machine Learning Data Lake, and Vector Store. showed a few experimental results, which is showing that it is ahead of the competition and performance is at par with in-database query processing. And it provides queries across OLTP warehouse and lakehouse with automatic schema generation and other bunch of features like vector processing and object resident files. So with that, I think I'm at the end of my talk. Thank you.
Use system like